Okay, so like we said last time, this is what we could have made, the 5.79, but we actually ended up making 1.39. So the last part of the question is going to be asking us how many grams of excess reactant are left. Okay, so what that means is we're taking a look at how much zinc do we still have inside of our, reaction. So what we're going to do is we're going to take the amount we could have made, and then we're going to subtract how much we actually did make. So we're going to do 5.79 grams minus 1.39 grams. And 4.4 grams, I think I explained this last time. This is the amount of zinc 2 nitrate that we did not make, right? Okay, this is what we could have made if we had no limiting reagent, but we did not make 4.4 grams. All right, so from there, we just do stoichiometry backwards from zinc 2 nitrate to find how much zinc is left over. So you actually have the numbers for this already. I'll just set this up kind of quickly, but we would just convert this into moles. So we would use the molar mass, 189.4 grams of zinc 2 nitrate per 1 mole. Okay, we'll use the balanced chemical equation. We have 1 mole of zinc 2 nitrate for every 1 mole of zinc. And then all you have to do from there is turn 1 mole of zinc into the grams, 65.41 grams. And then whatever value you get from there should be how much we actually have left over. So I'll give you guys a practice problem to work on, but just to reiterate, we subtract how much we could have made versus how much we did make. That's where we got 4.4. That's what we did not make. And then we just need to do stoichiometry, find out how much zinc is still left over. That's it. And then for the final answer, if you guys punch it in, you should get 1.5 grams of zinc. And that's how much we have left over. All right. All right. Any questions on any part of those calculations? I know you guys are still copying it down, but if you have questions, please let me know. Or is it pretty simple? Stoic is easy. Expecting 100% on the test. Because it's a lot easier for me to grade when there's nothing wrong. Huh?
Did Jordan take his test yet?
No. So Jordan is the reason the test can't get passed out today. Come on, Jordan. Okay, but before we move on, we're gonna just talk about very briefly theoretical, actual, and percent yields. And so I'm gonna just very briefly go over what they are. So theoretical yield, an easy way to think about this. This is how much you can make in theory. So this is the number that you get from your stoichiometry. So if you do all your calculations, whatever answer you get, that's your theoretical yield. That's what you could make in theory. Okay, but in real life, you can never make the theoretical yield because chemistry is just not 100% efficient. Sometimes the chemicals won't mix all the way. You make errors as a human. There's material errors, things like that. So we determine the amount that we actually make, called the actual yield. So this is what we get in real life. And then the percent yield is basically just the percentage that you make in real life compared to the theoretical amount. So this is the equation for the for percent yield. It's pretty much just another percent formula. It's what you actually made divided by what you could have made times 100%. Okay, so hopefully in your previous chem classes you learned about these theoretical, actual, percent yield, but this is just a way for us to compare the numbers that we get in the lab with the amount that we actually make. All right, so that's just, and I think that's the last thing we're learning for this unit. It's just practice problems from here on out. So I will give you guys about 5-6 minutes. I want you guys to solve 3.19. It's gonna be stoichiometry. It's gonna be percent yield. So go try that out with the person next to you. We'll go over in about 4 or 5 minutes, and then we'll move on to some more practice problems. All right, so we start with 25 grams of cyclohexane, and then it tells us that we want that cyclohexane is the limiting reagent, so we don't have to do stoich twice. And it's just asking for the theoretical yield of adipic acid, and that formula is right here. It's given up here, but we also know it's not H2O, so there you go. So all we're going to do is take the molar mass of cyclohexane, so divided by 84. We use the mole ratio from the balanced equation, so 2 to 2. It's 2 here, 2 here. And then we just find the molar mass of adipic acid and 146 grams. Everybody got that? Okay. So for your final answer, you should get something around 43.4 grams. Okay, something around there. As long as you're in that ballpark, you should be good. Okay. And this right here, since this is the number that we got from our stoichiometry, is what we call our theoretical yield. Okay. So whatever answer you get from stoich, that's your theoretical yield. Okay. All right. Any questions about part A? Yeah.
That'd be a stupid question. But why does it have H1?
That is a stupid question. Why would you ask that? Imagine not knowing that. No, I'm just kidding. So the reason, so you're talking about right here, right?
Yeah.
So the reason why it's like that is because we're gonna talk about this later, but if you ever see the elements split up inside of the formula, it's kind of telling you what the structure of the molecule looks like. So there's two H's kind of on this side, and then there's hydrogens in the middle. And that's why they split them up. Does that answer your question?
Yeah.
Can't imagine you asking that. Imagine not knowing. Ugh. I'm just messing with you. You should. All right. So, no, that was actually a good question. All right. So let's go to part B. It tells you you actually obtain 33.5 grams. So that's what we make in a lab. So that's your actual yield. So 33.5 grams. We're going to divide that by our theoretical yield, which is 43.4 grams. And then all we got to do is multiply that by 100%, and that'll give you a percent yield of about 77.1%. Dude, 77% is actually a pretty good yield. I mean, it depends on what you're making. But I mean, corporations spend like millions of dollars trying to push up their percent yields by like 1 to 2%. Because if you make something at scale, that could be pounds and pounds of it, tons and tons over time, and depending on the drug, like millions of dollars. So there is a big incentive to make these processes more efficient. Yeah, that's pretty much what chemical engineering is. Yeah. I know. I could have been a chemical engineer, but
What's nuclear fusion?
nuclear fusion is basically where you take two hydrogens.
Like what major?
That's a lot of different fields. You would need chemical engineers, mechanical engineers, theoretical physicists.
30%.
Yeah, electrical engineers. Like, it's because it's to perform fusion. There's so many things that go into it. Yeah, I mean, it's a very broad field. All right. So we're going to move on now to 320. And this is going to be the last real problem for this workbook. We're just going to do practice problems here. And here we are going to be combining everything together. Okay. Everything. And then we'll do some practice problems that'll help you guys out for the exam. But I want you guys to spend a good maybe 6-7 minutes. See how much you can get done by yourself. If you're able to get this on your own, you're in pretty good shape, at least for the stoichiometry portion. And then for part D, I'll show you guys how to do that. But I mean, if you could figure that out on your own, that's great as well. Yes. Alrighty, guys. So this one, we start off with two different starting values. So let's do part A first. So we start with 100 grams of iron 3 oxide. So you got to figure out what the chemical formula is. It should be Fe2O3. Okay. And then we have 50 grams of carbon monoxide, and that's going to be CO. Okay. Now we do need to write the equation. So if we write the equation, it says 100 grams of iron 3 oxide, so Fe2O3, and carbon monoxide they produce solid iron, which is just elemental iron, and CO2. Okay, so that's your chemical equation. Any questions on that part? Okay. All right, so we got to balance it. So I'm going to balance it 3, 2, and 3.
Oh, you're so good.
I know, I did that right in my head. I definitely don't have it written down here. Okay. All right, so that's going to be the balancing. So just remember, guys, make sure that you start with the balancing because that will tell you your mole ratios. Okay. All right, from there, with my head, I'm going to do all the molar masses and the conversions. Okay, so you should get 159.7 grams for your iron 3 oxide in every mole. If you look at the equation, you have 1 mole of iron 3 oxide for every, well, it doesn't really matter which product you find. You could have done it with iron or CO2. I'm going to do it with iron because I don't want to add up CO2, even though I actually have that one memorized. Yeah. So you could have done it with either one. Okay, so we got 2 moles of iron, and then every mole of iron is going to be 55.85 grams of iron. Okay. And so we could potentially make 69.95 grams of Fe. Okay, if you did it with CO2, that's totally fine. You would just change the mole ratio and the molar mass, obviously. All right. Any questions on that part? The first one?
Okay.
Yes.
Not bad.
All right. So for the next one, we're gonna do it with CO this time. CO has a molar mass of 28 per mole. If you look at the mole ratio, it's 3 moles of CO for every 2 moles of iron. And then we're going to end it off with the molar mass of iron, which is the same thing, 55.85. Okay, and so that will give us a value of 66.49. All right, any questions on that part, the stoichiometry? So stoichiometry shouldn't be too bad. Obviously you wouldn't do it, as fast as me copying off the thing I already did. But you should be able to get those values on your own. Yeah, I solved these, dude. I solved these a long time ago. I solved them before you were born.
I thought you were like that's smart. How long have you been working with this room?
A long time.
No, that's not an answer.
I'm at least 100 years old.
At least.
At least. Okay, so what's the actual amount of iron that we made?
60.
Yeah, 66.49. This is the actual amount of iron that we made. Okay, so to answer part A, which compound is the limiting reagent? CO, because we run out of carbon monoxide first, and we stop at 66.49. All right, I do want to pause and ask again, does everybody go with that part, the stoichiometry? Everybody good? Okay. All right, let's move on to part B. Now, we actually have half the answer already. We found out that we can create 66.49 grams of Fe, but now we need to find the grams of CO2 that we need to make. Now, you do not need to do stoichiometry 2 times because you already know the limiting reagent. You know which one runs out first, right? You already know that CO is going to run out first. So you can just do stoichiometry with CO. So 50 grams of CO. Just copy it down exactly how you had it. 28 grams per mole. This time the mole ratio is 3 moles of CO for every 3 moles of CO2. And then CO2 is 44 grams per mole. And so that will give you a final answer of 78.57 grams of CO. So that's going to be the other one. So the point of that part of the problem was just to show you guys, once you find the limiting reagent, you already know which one's going to run out first. So you can just do stoichiometry with that one. You don't need to use the excess anymore. Okay. Any questions on that one? Again, we're just doing regular stoic right now.
Yeah.
We'll give you no break just for saying that.
Why?
Okay, let's move on to part C now. Now we're trying to find the leftover, okay? So for the leftover, we're gonna do what we just learned. We're gonna take this value right here, the 69 for grams of Fe. This is what we could have made. Okay, this is what we could have made. Okay. And then this right here, the 66.49, this is what we actually made, right? And so what we can do is we can take these two values, find the difference. So 69.95 minus 66.49. Okay, and if we subtract them together, we can figure out that we have 3.46 grams of iron that we did not make. All right, so from there, we can just work backwards and figure out how much excess is left over. You have 3.46 grams of Fe, and then we just work backwards to find the excess, which we said is Fe2O3. So we just work backwards. We can use the numbers that we had and then work back. So you got 55.85 grams of Fe for every 1 mole. There's 2 moles of Fe for every 1 mole of Fe2O3. And then every 1 mole of Fe2O3 has a molar mass of 159.7. And so you should figure out that the amount that you have left over is 4.95 grams of Fe2O3. And that's your leftover. Oh, so many numbers. All right, so before we do part D, I'll give you guys some time to copy it down, but please let me know if you guys have any questions about any of those values, any of those calculations. We probably won't do a problem this comprehensive for the rest of the lecture, so please get your questions out now. Yeah.
So,
Okay, so I'm going to erase this real quick just because I need some space. But for part D, what we have to do is basically use all of our numbers to prove that matter is neither destroyed or created. Okay, that, you know, it's balanced out. All right. Yes.
so basically, the reactants.
Yes, that just means the reactants and products will equal. So let me show you guys how that looks. So I'm going to start by writing the equation again. So you got Fe2O3 reacting with carbon monoxide to produce iron and CO2. So before I'm not going to balance it because it's not necessary. I'm just going to draw you guys another amazing picture so you can visualize what's going on, okay? So let's say this is our container for the reactants, and this is our container for the products, okay? It's beautiful. I'm going to even add a detail. It's a beaker. Wow. Okay. So let's look at the left container, okay? Give me one of the, so if you can raise your hand, give me one of the chemicals that's in that beaker. Yeah, Jordan. Yeah, carbon monoxide, so CO is inside that beaker, so this guy right here.
Also,
Yeah, iron 2 oxide is also in there, so this guy right here. Are there any other chemicals that we start out with? No, right? Okay. So they mix together, right? And then this reaction happens. So we know that obviously Fe is going to be produced. So they're going to react and they're going to produce Fe. And they're also going to react to produce CO2. Okay. All right. Are there any other chemicals on the right side? Yeah. So let's think about limiting reagent. Okay. So which one of these chemicals runs out as they react? Yeah, carbon monoxide is going to run out. But do we still have some leftover of the other one?
Yeah.
Yes. So on the right side, we actually have 3 chemicals. Fe2O3. So that's something to remember when you visualize these reactions, the excess, you're still going to have some left over when you're done with the reaction. Okay. And that's why we do all these reactant calculations. Okay, and it's because we still have it at the very end. That's why it's called excess. Yeah.
Does that just stay there in the form of a homogeneous mixture?
So we're not going to talk about homogeneity right now, but it's still there. Yeah. Okay, so let's look at our numbers now. Okay. So let's go through this. How many grams of iron 3 oxide do we start with? Yeah, it tells us 100 grams right here. So we're going to start with 100 grams. How many grams of carbon monoxide do we start with? 50 grams. So what's the total mass of the reactants? 150. Okay. So far, so good? All right, let's go to the right side. Okay, let's start with the easier one. How many grams of iron do we make? Yeah, 66.49. How many grams of CO2 do we make? 78.57 grams. And how many grams of Fe2O3 do we say we have left over?
1.947.
Yeah. About 4.9. And I got 5, but something like that. Okay. All right. So I want you guys to calculate how many grams of total product we have. Yeah, 150. I know it's magic, right? Whatever. That's your rounding. So you got 4.95 plus 66.49 plus 78.57. 150.01. That's because of a rounding. Okay, but 150 grams. And that shows you that as the chemicals react, you're going to have the same amount of product as you do react. Okay, matter is neither created nor destroyed. Okay, and that's it. That's the law of conservation of mass, and that's how we can prove it using stoichiometry. Yeah.
We have to like prove it like this.
No, I'm not gonna ask you this on the test. They'll probably won't. But you might have to like show your numbers and just say like reactant total mass is 150, product total mass 150. That's kind of how you can demonstrate it. But no, you don't have to draw this picture.
Yeah. Are the AP people gonna ask you for it on the test?
I've seen this on the test before. Yeah. All right. So let's do. You guys want to take a break now or do a similar to a test problem first?
Take a break now.
Okay, let's take a 5-minute break and then we'll do one last problem. All right, we're gonna move on to 321. And this problem right here is it's an easier version of the FRQ that's on your test. Okay, so I am giving you guys a big hint on how to prepare for this next test. I know I promised I wouldn't, but I don't know. There's just something about you guys where it just melts my heart a little bit and makes me want to help you guys out. No, I'm just playing. Anyway, so yeah, 321. Again, it's an easier version of the problem that's going to be your FRQ. So let me yeah, I'm just going to go over it because it is different from everything that we've seen, and it can seem a little complicated, but it's honestly not that bad. Okay. All right. So it tells you that a combustion analysis of a hydrocarbon produces these products. Okay. And then they want you to find the empirical formula of the hydrocarbon. Okay. So you're like, dang, what the heck does that mean? So some terms. Hydrocarbon basically means a chemical that's made out of hydrogen and carbon. Right. Super good naming, right? So you have a chemical that's made out of carbon. You don't know how many carbons there are, and you don't know how many hydrogens there are, but you just know that it's made out of carbon and hydrogen. Okay. It's reacting with, or it's in a combustion reaction, which means that the other reactant is going to be O2. Okay. So far, so good? All right, and then they're going to react and they produce CO2 and they produce H2O. And then specifically, it gives you the numbers. You got 33 0.01 grams of CO2. And you have 13.51 grams of H2O. All right, so far so good, guys? All right, so what this problem is basically asking is the empirical formula of the hydrocarbon. Now, if you guys remember, empirical formula, the point of the empirical formula is to find the mole ratio between the elements that make it up, right? What it's made out of. Basically, how many moles of carbon are there relative to the moles of hydrogen? Make sense? Okay. Now, some of you guys might actually be able to see this and find the answer right away just on ratios, but I'm going to show you guys the real way to solve it just because the harder question on your FRQ is going to require this method. So let's kind of analyze this equation. Now, there's two reactants and two products. Okay, but we can find out a lot of information from this. If you take a look at the chemical we're interested in, carbon and hydrogen, okay? The first element that makes it up is carbon, right? But if you take a look on the right side, carbon is used to make only CO2, right? And so what that means is all of the carbon that you start with ends up inside of CO2. Does that make sense? Okay. And all of the hydrogen that we start with ends up in H2O. Does that make sense? So if you can figure out using these two numbers, how many moles of carbon are in CO2, you can find out how many moles of carbon were inside of the original compound we're looking at. So I'm going to show you guys how to do that, and then I'll have you try hydrogen on your own, and then see if you can find the empirical formula. So let's take a look at CO2. It tells you that you end up creating 33.01 grams of CO2. And so what we're going to do is we're going to use that info to find out how many moles of carbon there are. So super simple. We know the molar mass, 44 grams of CO2 inside of every mole of CO2. Right? And then we're interested in the moles of carbon. So 1 mole of CO2. How many moles of carbon are there in 1 mole of CO2? Yeah, just 1. So 1 mole of carbon. And so if you solve that, you can figure out how many moles of carbon are in 33.01 grams of CO2. And consequently, that's the amount of carbon in the entire reaction. Okay? So we're just going to punch that in our calculators. So that means 33.01 divided by 44. Going to give you about 0.75. So we'll write 0.75 moles of carbon. So there are 0.75 moles of carbon inside of 33 grams of CO2. And since all of the carbon in the reaction was used to make CO2, you know that there are 0.7 moles of carbon inside the original hydrocarbon. So this will be 0.75. Does that make sense? All right. Yes.
Wouldn't you like, I know like a few days ago, said like
Yeah, you'll have to change it to a whole number, but you'll need the other one in order to change it up. Yeah.
What about like but I feel like so I don't know like energy or something gets lost in a reaction, so
Yeah, so this is why it's a theoretical thing. In real life, yeah, there is going to be some lost, but we're working in a perfect world here where unicorns are real and candy grows on trees, and you don't know me. Okay, so we're going to do the same thing for hydrogen this time. So if we take a look at hydrogen, all of the hydrogen is used to create the water, right? So that means 13.51 grams of hydrogen or H2O contains all of the hydrogen. So there's 18 grams of water in every 1 mole of water. And then we know that inside of 1 mole of water, how many moles of hydrogen are there? 2. It's 2 moles. Because if you take a look at H2O, there's 2 hydrogens inside 1 water. Okay, so just be careful about that, because the mole ratio is going to depend on the chemical formula. Okay, so plug it in, 13.51 divided by 18 times 2, and you should get about, let's do 1.5. So 1.5 moles of H. What's up?
Do you mind if I leave class like a couple minutes?
That's fine. Okay, so that means that the other question mark is 1.5. Everybody good? Okay, now we can finish up this problem by dividing by the smallest number, which is 0.75. And so some of you guys can do this in your head, but 0.75 divided by 0.75 is 1. So C, 1.5 divided by 0.75 is 2. So your empirical formula will be CH2. And that's it. So your FRQ on this test will be a harder version of this. So please just make sure that you guys are comfortable doing these problems.
Why did you divide both by
Because we need to make it a whole number. Yeah. Which one? For the final answer? Yeah, we got 2 because you see right here. You're okay with this part, right? How we got these numbers. So the smallest number is 0.75, right? So we need in order to make an empirical formula, we need whole numbers. So we divide 0.75 by 0.75. So that's going to be C1. And if we divide 1.5 by 0.75, that should be 2. So just divide the 1.75 by 0.75. And that'll give us 2. Oops, not C. Does that answer your question? Okay. Yeah, so that's the empirical formula. Just divide by the smallest number.